So under this section, we are starting it again, and today we have a target to understand how the current flows through PN junction. As in the previous class, we talked about that when a simple type of semiconductor material is diffused with certain, just. So we basically have a target today to understand how this current starts flowing to a PN junction. If suppose we go back, we talked about that how this P and N junction is created. So this is a very simple, very easy phenomena. You just take a simple piece of semiconductor and dope it from kind of a doping. If you are giving acceptor kind of a doping here, so the first layer will be created as P-type material and the substrate you are using as an N substrate. So here in between a junction is created. Second thing, once this fabrication process is completed, the second thing comes, if suppose this situation happens, then semiconductor which were having a N-type material and semiconductor which were having a P-type material having different type of energy band gaps. P-type के और N-type के दोनों के अपने अपने energy band gaps थे, उनके अपने अपने energy structures थे. So when they meet with each other, जब वो एक दूसरे से मिलते हैं, then what happens with the energy band gap structure? So we studied about that. We talked about in the previous lecture. Now, if suppose we have a simple type of PN junction, let's try to understand what is the process by which we have a flow of current. So let's begin with this one. If you see the first diagram, in this diagram, at this particular diode, which is created as a PN junction, and the two electrode has been taken out. As we are taking two electrodes out, that's why we are calling it diode, double electrodes. So we have one and two electrodes. The side which is connected with the P is called as a P electrode. The side which is connected with the N type of material is called as N electrode. Once this is available freely, when nothing is connected across these two terminals, then we say this is a simple PN junction. And during this PN junction, it happens that this particular diode creates a depletion region at the junction. This is a very natural phenomenon. And we talked last time that how this depletion is being created. If we see in this stage, this particular equation, then what happens in the terms of the energy band? So we have conduction band, we have valency band, and this is a very, very important. We talked about this phenomena that in N-type material, this has a lowering stage. It means conduction, if suppose in P-type material, conduction can be done at 2 electron volt, then in N-type material, this conduction can be done only at 1 electron volt. So that's why this EC has high range here, and this EC in the N-type material has a low range here. So this is being matched. And here we have this Fermi energy level, which is making it in an equivalent situation. As we talked, it happens when they meet each other. So here we are having a large number of electrons and we are having a low number of electrons here. So electrons move from this point to this point from this situation. And similarly, it happens oppositely in this direction also. So this kind of a movement from this point to this point and opposite in the reverse direction will create a depletion and a potential barrier has been generated. So at this stage, if we see this diagram, we can say the potential barrier is generated and no further transmission of electron and holes takes place. This is exactly the first state we called as free state or zero biasing state. Most important, you can say like that. It's a very, very good word. Zero biasing state. So it is zero biasing state. You can say this state comes up here. Then coming to the next, what happens when we are applying a certain electric field or potential across this diode? So you see here in this diagram, we are applying a certain electric field in such a way that P terminal is connected with the positive and the N terminal is connected with the negative. So this P and N, when connected with the positive and the negative, then this P is receiving a repulsive force here because P having a positive charge carriers and this is a positive terminal. N's are having negative charge carriers. It is connected with the negative terminal. Then the forces experiences a force and starts moving towards the center. And that happens same in this case also. So under these two conditions, we have the same one, and in both the condition, because of the situation, they starts moving towards the junction. But at the junction, there is a potential barrier which stops. They says no, you cannot allow to go from N to P and P to N because I have a potential barrier here which is opposing. It's a barrier like the barrier you have at railway station. Very same barrier. It's a closed. It is does not allow. And depletion region still maintains. So what we have to do? We have to apply a certain electric field in such a way, certain external potential in such a way that overcome this potential barrier. It means the barrier either it can be make it on या तो barrier हटा दिया जाए या barrier को तोड़ दिया जाए. तो तोड़ने का प्रोसेस कैसे है? जब आप उस बैरियर से ज्यादा बाहर सप्लाई क्रिएट करेंगे. When you're providing more electric field here, then this situation will appear that this barrier will be broken up. टूट जाएगा, खत्म हो जाएगा, nullify हो जाएगा. And when this becomes nullified, the holes from this section, it means holes here in the valency band, starts moving towards the valency band of N type. और जो electrons यहाँ के होते हैं, that starts moving to the conduction band of this type. So from here to here, electrons moves in conduction band and holes moves in valency band, and electrons reaches to this point, holes reaches to this point. By this, junction will have a transition of both electron and hole from one end to another. If we see the same thing in this diagram, then we see here that kind of a things happens, that this is basically the Fermi energy level, and here we see the EC. So this has a shift. Energy levels have a shift in their values so that the electrons and holes can easily transfer from one terminal to another terminal. And this kind of a channel path situation has been created. This situation has been created, and this channel path situation is called basically a kind of a phenomena over which a channel has been created. In this channel, electrons and holes takes transmission. So holes are moving here and electrons are moving here through this energy band. And if suppose we do just reverse of it, now coming back on this one and doing just reverse of it. Now in this situation, we are applying the voltage, but just opposite voltage. It means the negative charge connected to P and positive charge connected with the N. So this negative and the positive will be attracting each other. And that's why the electrons will be feeling a movement towards this terminal. So they will be moving like this. And holes will be feeling a movement like this one. Under this situation, they will support barrier. If suppose we have a railway crossing and the people are just standing away, so they are increasing the depletion region. No person is there because the barrier is creating a depletion region. You stay here, you stay here. And if suppose the people are just going reverse, then definitely this depletion will be increased. So under this situation, this depletion is increased. And when this depletion is increased, then definitely the junction will have more transmission of charge carriers. If we see such situation here, then what happens? You see here the diagram. Under this situation, this Fermi level lies on exactly on valency band. And here in the conduction band lie on this one. So they are having a perfect mismatch. And the electrons which wants to go here requires too much of energy. This is what energy. Q VBI plus VR. This is the amount of energy required to move to the conduction of P type. इतनी energy चाहिए उनको यहाँ N type के conduction band से P type के conduction band, which is too much. वो नहीं मिल रही है उनको, है ना. यहाँ पे potential barrier और reverse biasing दोनों इसको मिलकर add up हो रही है. और यहाँ पर क्या हुआ था? We have here the reverse biasing and the forward biasing and the potential barrier. दोनों एक दूसरे को cancel out कर रही थी, यहाँ एक दूसरे को support कर रहे हैं. So that's why this gap has been created. And here this has been lowered up. So if you see here, in this situation, this gap for this movement has been lowered. That has been lowered here. And in the reverse bias, this has been created much. So it requires high energy to go from conduction band of N type to conduction band of P type. So because of this situation, more majority charge carriers transmits from one terminal to another terminal, moves from one section to another section. This is exactly the importance of biasing. So first, zero biasing phenomena. Second is the forward biasing. Under the forward biasing, they can move from here to here, holes valency to valency, electrons conduction to conduction. Similarly, in the third stage we have what? In the third stage we have holes and electrons separated and segregated from each other, and under this segregation they create a depletion, and the depletion increases. And that's why if you see here in this energy band diagram, it is defining so nicely that this energy band diagram has created a big difference because these two potentials are supporting to each other. That's exactly the three-state situation. So I'm just leaving this section open to ask if you feel any question is here. So well, like I'm just repeating this section again, like forward, reverse, and zero biasing. So important. So when first of all, what is PN junction? The PN junction is one of the simplest device that has been created with the help of what? With the help of semiconductor material. We have used two different type of semiconductor material, P and N. So because we are having a masters, so under this situation we talked about their energy gaps. So coming up first situation, when this PN junction is made ready. So like if we have, so if you see we have a large number of components, I'm just showing up here. So here we have, I'll show you, it's kind of a diode, yes. Yes, so if you see it's a very small, I suppose whether you would be able to check it or not, small black part is which is in the diode being connected. So such kind of a diode when we have in its position like under this kind of circuits, we have these circuits also. I'll check whether I do have any diode with me or not. So I'll check and later on will tell you. So if suppose we have a simple diode and it is not connected anywhere, then this diode will called as a zero bias state. Under the zero bias state, it is a very same as we talked previously. It has a depletion. इसके पास में क्या होगा? अपना depletion region बना होगा. Depletion region बनने का मतलब क्या होता है? Depletion region, it means potential barrier, which is opposite. So if you see here, this QVBI, this is the gap. This gap is indicating that is this electron requires this energy to reach to conduction of P type. Similarly, here in this case, the same kind of a thing happens in the case of this one. So this gap is indicating the conduction can be done, but only when you have certain energy. So this is called as a potential barrier, which stops. Second condition, जब हमने forward bias किया तो forward bias में we are applying this VF and this VF VBI potential barrier and this one is opposing each other. Potential barrier को खत्म कर देता है. कौन खत्म कर देता है? The external potential difference. The external potential difference is opposing. Each other, and in this situation, then what happens? This barrier has been removed, and the energy is sufficient. This energy is sufficient to make an electron from N type के conduction band से P type के conduction band में पहुंचाने के लिए अपने आप में it's more than sufficient. It's sufficient. Then in the case of in third case, potential is applied in such a way that it oppose कर रहा है. Oppose कैसे कर रहा है? इसका मतलब in this condition, this negative is connected here and P are the positive charge. So they will go away from the junction. They will not move towards the junction. They will go away from the junction. And while they are moving away from the junction, then what happens? This and this both will be segregated. This will be segregated so nicely. And under this situation, this segregation will create a high depletion region. Let's check the energy gap. So if you see here, this is the conduction area. This is the conduction area of holes, P-type material, and this is the conduction area of N-type. So if you see how much energy is required, it's too much. QVBI, it means potential barrier plus this voltage. So that much amount of energy is now required to make an electron conduction of N to conduction of P. So this gap has been created. ये gap create हो जाता है. इसकी वजह से इलेक्ट्रॉन एनर्जी बैंड गैप में ट्रांसफर नहीं कर पाते. बस सीधी सी बात है. एक खड़ा है ग्राउंड फ्लोर पर, एक खड़ा हुआ है फर्स्ट फ्लोर पर. तो ग्राउंड फ्लोर से फर्स्ट फ्लोर के बीच में या तो सीढ़ियां चाहिए, या तो आप सीढ़ियां उनको प्रोवाइड कीजिए या स्लोप दीजिए. सो सीढ़ियां और स्लोप दोनों ही अपोजिट हो गए. सो सीढ़ियां तोड़ दी गई. दिस इज अपोजिट काइंड ऑफ फील्ड इज देयर. इसमें सीढ़ियां दे दी गई या स्लोप लगा दिया गया. सो दैट्स व्हाई इट इज राइजिंग अप इजीली. सो दैट हैपेंस हियर. So this is exactly zero bias situation, forward bias situation, and the reverse bias situation. So I hope you now able to understand. So we have a same, but in a different way, in a different aspect. If you see here, so N-type and P-type material combination is here. If you see here, these basically bubbles are indicating the holes, and these pink shade, it shows the dynamics because they are highly moving. So that's why they are the dynamic. So this is basically, and such kind of a junction is called as a PN junction. So energy band, I already shown what exactly happens in the energy. But if we see it two-dimensionally and try to understand, then the situation happens like this one. So when we were talking about the same one, now it will have a more visibility to make you understand. So once we start, just we connect the junction and we are providing nothing to it, they starts moving. Now, if you see this movement, if they are moving from here to here, this is called as a diffusion process, natural movement. And this diffusion process is what? Conduction band. See, the conduction band to conduction band. So this electron is moving from conduction band of N to conduction band of P. It's not moving like entering into the between the holes like not. It's not mixing it up. Mix नहीं हो रहे हैं कहीं. कहाँ जा रहे हैं? Conduction band of N से conduction band of P की तरफ जा रहे हैं. ऐसे ये holes जो हैं वो वैलेंसी बैंड ऑफ P से वैलेंसी बैंड ऑफ N की तरफ जा रहे हैं. जैसे ये मूवमेंट स्टार्ट होता है, वी टॉक्ड अबाउट दैट, इनके चार्ज सेपरेशन की वजह से एक पोटेंशियल बैरियर जनरेट हो जाता है और वो इस तरीके से पॉजिटिव पोटेंशियल्स टुवर्ड्स दिस वन एंड नेगेटिव पोटेंशियल टुवर्ड्स दिस वन. And this positive and the negative side of potential will help us. So basically, if suppose we are connecting a simply a semiconductor material like a PN junction, so first of all, first phenomena happens which is called as a diffusion phenomenon. This phenomena is called as a diffusion phenomena. Under diffusion, high concentration to low concentration movement, conduction to conduction, and valency to valency. That happens. Simple. And after some time, situation happens that here an electric field is set up and this electric field opposes further and no movement is there. So the electrons stays here in conduction band of something, P-type, and conduction band of N, and no further movement will take place because the holes will be getting an opposite electric field. This electric field is being set up from this positive, so they cannot move off here. And electrons will be feeling because of this negative, they cannot move off here. So this creates basically a depletion region. So no charge carriers are there because of this electric field. So this is the first phenomenon, diffusion. Now talking about the second phenomenon. Second phenomenon is what? The drifting. Once so this is basically the very beautiful diagram, but that is making you very much clear that if suppose that is happening, so this is shifting up. This is basically called as a shifting up. So here in N-type material, we have a majority charge carriers as electron, and in P-type it is minority. Here we have the low concentration, high concentration, they starts moving. Similarly, here we have holes are moving from this type. So this is a situation of zero biasing. And after some time, this depletion region has been created. That I already told you. Such depletion region has been created and they stop. Now in that, what is basically the recombination? When an electron is moving from high concentration to low concentration and losing its energy, important point, losing its energy. So when it loses its energy, it comes down from conduction band to valency band. Only then recombination takes place. So recombination does not take place like the previous diagram if we see here, and we get confused. They are moving here and they are having the hole, they can easily recombine. Not like that. It is actually movement like this. They are moving here because there is a huge gap. They cannot recombine. They only recombine when an electron loses its energy and then becomes low energy particle. Then he try to find out where is the hole. I can just sit over there and get relaxed. So that particular electron create recombination until unless nobody. So if electric field is applied, then again this is start conduction from here to here. They will not recombine with each other. So only recombination takes place when they loses their energy. So this is exactly the meaning of this one. So let's see, now we have a target to basically understand about how this voltage and current, how this voltage and current relates with each other if suppose we are applying, because you see, we talked about in three stages. First, no bias, second, forward bias, and third is a reverse bias. So if you see here in this one, the potential barrier is here when there is no field applied across this one. And if you see here, we are applying certain potential. So anybody can easily tell us like this is the forward bias situation. And when this forward bias voltage is quite enough, more than this potential barrier. Now the question comes up that suppose we have a silicon piece of material. So what will be this potential barrier? So you see here in this line, bias must be greater than barrier potential 0.3 volt for germanium. So it is only 0.3 volt for germanium and 0.7 volt for silicon. So if you want to remove this depletion region, how much voltage you have to put on? You have to put on more than 0.7 volt for silicon, more than 0.3 volt for germanium. Then it only becomes forward bias. And once it becomes forward bias, the movement becomes like this one. So under this situation, if we see here, this depletion region gets on removed. So now we have a target to understand when this happens in the case of the reverse bias. So when the reverse bias you are providing, it is supporting, and this kind of a situation has been done. So if you see here, this gap has been increased. So let's check it out. Suppose we are looking, let's check if suppose we are providing a voltage, whether the current is flowing or not. So this is a very simple kind of a circuit has been created. In this figure, if you see here, we have PN junction diode. This PN junction diode is connected with the voltage, which is called as a bias voltage. Here we are applying this voltmeter. This voltmeter is indicating that here we have some voltage potential. Third, we are connecting here the ammeter, which is indicating the current, forward bias current. That's why IF is written. VF, forward bias voltage, and here is the bias voltage. Now, if suppose we are changing this bias voltage, then it will become the forward bias. Let's see. Now, this is very important. Under forward bias situation, what happens? So this is very, very good, which is called as a VI characteristic. It's not a new one. It's like an old one. If you see here this VI characteristic, so initially when you are applying a forward bias voltage and you are increasing, see what is the figure here? It is current IF, forward bias current. Here it is VF. So if you increase the current up to a certain level, it is rising so slowly. Reason, up to 0.7 volt, there is almost no current. This current is milliampere. And you see here, almost no current because electrons are not capable to move on from P to N, N to P. Almost negligible. Once the voltage is increased more than 0.7 volt, then there is no junction, there is no resistance, and they will start flowing like this one. So this is basically called as VI characteristic. This tells us that this depletion sustains until unless we are providing 0.7 volt. And beyond that, if we are providing, then this junction will be removed on, this depletion will be removed on, and there will be adequate flow of current like this one. So this is exactly the part. So I will take this VI characteristic more elaborative in the next lecture. I hope so. In the three state, first zero bias, second forward bias, and the third reverse bias. Under three state, you are capable to understand by illustration movement, what kind of a movement, and second energy gaps, which are very, very important through energy band gap. So that's exactly important to make it understand through this energy band gap that what happens when they are having a depletion region. So this is exactly the depletion region that stops. And when reverse bias situation comes, the depletion region creates much bigger and this difference has become much bigger. This is exactly my today's target. So I hope so. Under these three conditions, zero, forward, and reverse, you are capable to understand. Now, this session is open for your questions. And the next session, we will talk about basically the